Hello students. So we have started the chapter solution and we have done 3 classes on it. So today is the 4th day of this chapter. So let me revise those things first of all. So the chapter that we have started was solution. So started with the types of solution, what is solution, then we move to the types of solution, and we have seen that we can have different combinations like we can dissolve solids in liquids, we can dissolve liquids in liquids, we can dissolve gas in liquids, and similarly we can dissolve all these three in all these three. Basically means we can make one solvent and one solute. It was like this. So we have seen that yes, there are multiple types of solutions that are possible due to the combination of all these three states. And then we move to the types of solution specifically, right? For solids and liquids, we have seen some concentration terms. So those concentration terms you can consider in general also. There's no problem in considering in general. So when I talk about these concentration, we basically dealt with this molarity, molality. Molarity was the number of moles per unit volume. Molality was number of moles per kg of solvent. Then we move to this mole fraction. So it was number of moles by A, for which we are considering the mole fraction by the total number of moles, right? Then we have seen that if we add all those mole fractions, that is summation of the mole fractions, then we will get one. And we have to consider all the components. So if you have a binary solution, means we are having two components of that solution, then we will say that chi A plus chi B is equals to 1, where chi A and chi B are the mole fraction of A and B of both the component, you can say. Likewise. So this was the thing. Then we have seen the solid in liquid solutions. So in that we have seen that yes, there are two factors. So one of these was temperature and pressure. So we are basically studying these two factors right now. So if we talk about this temperature thing, so this temperature has a positive effect on the solubility, right? So if we increase the temperature, the solubility of solids and liquids increases. This was the one thing, important thing you can say, and the vice versa is also true. But the important thing which I want to put your head in, it is that if we have prepared a saturated solution, so by saturated solution I mean that no more solute can be dissolved in that solvent at that given particular temperature. So if we have a concentrated solution, then we will say that the concentration of the solute will be the solubility of that solute. Now what you will ask that what is the solubility? So you must have studied this solubility term in the equilibrium. So those who have not studied, let me make it clear for you. So it is basically the solubility is basically related to solubility product, which is the product of the concentration of a partial, you can say partial soluble salt. That is a different thing to consider. But right now you can consider that if we have a saturated solution and the solubility of this, sorry, the concentration of the uh, say solution is x, then x will be also its solubility. Now this was all about solids and liquids. Then we move to this gas and liquids, where we studied that okay, both temperature and pressure have effect on this thing. Yeah, one more thing. When we were studying solids and liquids, we have considered that effect of pressure is negligible for that kind of solution, because solids are, you can say they are negligible, or you can say negligibly compressible, close to non-compressibility. Yeah. So it has a no effect, means pressure has no effect on the solubility of solids in liquids. Yeah, so this was the thing. Next we move on to this gases and liquids, and we have seen that yes, pressure has a direct effect, or you can say true effect with this solubility of gas in liquid. So when we increase this pressure, the solubility of gases and liquids also increases. And this was governed by this Henry's law, which says that the partial pressure of that thing, gas, is equals to kh times the mole fractions, where kh was Henry constant, and I have told you that it is gas specific, means it depends upon gas, or you can say it varies from one gas to another, means it will be one for oxygen, different for nitrogen, and likewise. Then I have said that if we have a greater value of KH, then we will have less solubility. Means a gas having a greater value of KH will be less soluble, and the vice versa is also true according to the formula I've told you, which is Pi equal to KHXI. Now, if you move to the temperature, so the temperature says that if we just increase the temperature, the solubility will decrease because the gaseous molecule will have the kinetic energy to escape this liquid phase and move to the gaseous phase, right? So this was gases and liquids. Then we move to this thing called liquids and liquids, where we have seen that uh, what is the effect of pressure, which was governed by this Rawls law, right? So we in that type of solution, we have considered one thing, that we are taking a binary solution. This thing is applicable in all the solution that we're considering. Plus, it is homogeneous. And third, the most important thing, that both of these components are volatile. Then and then only the Rawls law will be applicable to each of this. So if you have to apply the Rawls law on any of those component, I'm not saying that both of the component need to be volatile for applying Rawls law. I am saying that the component on which you are applying Rawls law must be volatile. So volatile substance are only this Rawls law is only applicable to this volatile substance. So this was the thing, and the formula was like this, that Pi is equals to P naught I Xi. What is Pi, P naught I and Xi? So Pi is the partial pressure again, Xi is the mole fraction again. Now what is this P naught I? So since we are considering the partial pressure of the gas or the vapor phase of the solid particle or the component, so if we take that component in a pure form, not in a solution form, then the partial pressure exerted by this component will be the P naught I, or the pressure due to pure component, right? So this was our Rawls law. Now, since we have taken a volatile substance, the vapor will be introduced of both the substances above the solution. Now, this vapor will exert pressure on it. So the total pressure exerted by both the components, means the sum of the pressure exerted by both the components, will be considered as P total. And P total is related to this mole fraction of the gaseous phase. So the point here I am telling is that the Rawls law I have told you earlier, and the mole fraction that was mentioned there was the mole fraction of the component in the solution or in the liquid phase, right? But when we talk about the gaseous phase, then the mole fraction in the gaseous phase will be given by Pi is equals to P total by I, where Pi is the partial pressure again of the vapor phase, P total is the total pressure, and Yi is the mole fraction of that component in the gas phase, right? So this was the thing, and we have seen some formulas also, so you can move back and see those formula. It was like 1 by P is equals to 1 by P total, something like that. Okay, so you can move in the previous classes or see the previous classes and relog those formulas. So this was this thing, it was over. So in the yesterday's class, we covered all this Rawls law and all. Now today I will be moving to this, say, the ideal solution and non-ideal solution, right? The ideal solution and the non-ideal solution, we will see azeotropes, and we will also see what is this colligative property. So this is the syllabus that we are having. So if I underline the syllabus that is covered with the green pen, so it will be, this thing is covered, this is also covered, and this is also covered. So we have covered up till this point. Now today we will be looking on this colligative property first of all, and it is not mentioned here, I think, in the CBSE syllabus, but this Rawls law is complemented with this ideal and non-ideal solution. So we will also study Rawls law. So I have a detailed syllabus here also, topics that we will study. So first we will see what is ideal and what is non-ideal solution. Then we will see the types of non-ideal solution, right? So these types are positive deviation and negative deviation. Moving on, we will see a less famous topic but interesting one called as azeotropes. At last, I will move to colligative property. So I will just give an introduction of this colligative property. I will not move to the types of colligative property right now. We will see that thing in the later on lectures. But for now, we will just see a brief introduction of this colligative property. So first of all, I've put this whole ideal versus non-ideal in a table, and you have seen this tabular form in one-on-one form here and there also. So it is mentioned all over the internet and the books. But let us make it clear, right? So the first and the main basic difference between the ideal and non-ideal solution is that the intermolecular forces is negligible in ideal solution. What is this intermolecular forces? So this intermolecular forces can be varied, like it can be dipole-dipole interaction, means the two dipole are interacting due to the electrostatic interaction. So suppose you mix two type of solute and two type of component, and they both were polar, right? So the molecular force that will be between them, inter means between two molecules, and molecular means between two different molecules, right? You can say. So the forces that is existing between two different molecules are called intermolecular forces. Now they can be dipole-dipole interaction due to two dipoles, right? They can be van der Waals forces. They can be induced dipole-dipole interaction, and many more interactions are possible. But the thing we are considering here is that the intermolecular forces should be negligible. So we are saying that it should be negligible in case of ideal solution, meaning that should be the interaction should be not that effective. Now, if it is significant, means the interaction is significant, means it is showing a kind of great attraction between these particles or repulsion. In either case, we will say that the solution is non-ideal. Now, ideal solution will follow Raoult's law. We will see how this Raoult's law is, you can say, violated due to the presence of this intermolecular forces. And the vice versa is true, that it deviates from Raoult's law. Now, if you talk about the enthalpy of mixing, it is zero. But the enthalpy of mixing in case of non-ideal solution, it is non-zero. Okay, so why it is zero? Because now the particles are not interacting, so no energy exchange, no energy exchange, no enthalpy change, no heat exchange, and no heat exchange means no entropy change. Okay, so no enthalpy change. So this is the thing. Now enthalpy of mixing can be zero or non-zero both. How? If the process is exothermic, it will be non-zero and non-zero are positive and negative both. So if it is exothermic, it will be positive, and if it is endothermic, if it is exothermic, it will be negative, and if it is endothermic, then it will be positive. Next, we have entropy of mixing. Then entropy of mixing is positive. In this case, it is negative. Next is the volume change upon mixing. So it should be zero, because see, the thing is that if we have a kind of interaction between the between the particles of both the components, right, then they will be coming closer or moving apart. In case of repulsion, they will be moving apart. In case of attraction, they will be moving close. So if the particles move close enough, then kind of compact solution will be formed, which will reduce the volume that was expected. So V1 plus V2 must be same. So if you have to consider a volume, it is V3 and it is formed by mixing V1 and V2, then it must be V1 plus V2. But since there is a kind of interaction in an ideal solution, so these particles will move closer and will result in non-zero volume change. And if it is zero, it is ideal solution. Talking about the colligative property, so we have not seen it right now, but we will see it later. So if the colligative property formulas are followed, it will be ideal solution, and if it is not followed, it is non-ideal solution. Then about solubility, it will follow Henry law. The ideal solution will follow Henry law, and the non-ideal solution will deviate from this Henry law. So you know this Henry law. It is Pi Kh Xi. So how you will know that it is following Henry law or not? You will simply plot a graph like this. Okay, we'll plot a graph. You've seen this graph in the Henry law class also. So if you plot it like this, Pi and Xi, and just you have to put the data points. So if the data points show a linearity like this, suppose the data points comes in this fashion. First one is here, second one is here, third one is here, fourth one is here, and fifth one is here. So suppose this show us a linearity, or you can say direct proportionality. So you will say that okay, this is the ideal solution. Now suppose we plot a graph and it goes like this. Okay, it goes like this. So the first plot is here. Okay, it is directly varying. It is true. Then it starts bending in a fashion. And you get this type of plot. Then you will say that okay, this is a non-ideal solution. So you can just verify that something is ideal or non-ideal by plotting a graph between Pi and Xi. So this was the difference between ideal and non-ideal solution. Next, I will make you more. I means I will make you more knowledgeable about this non-ideal solution. So basically, we will be dealing with two type of non-ideal solution. The first one is that it shows positive deviation, and the second one shows negative deviation. So let us see how. So this graph you have seen it earlier. Yeah. So this is the graph you have seen it earlier also. So if you look closely to this graph, this is the ideal behavior that we are expecting. Okay, so following the Rawls law, it should look like this, the green one. Yeah, so this is the ideal case. Ideal case. But since the non-ideal solution does not follows Rawls law, so we do get this type of graph, which looks like this. It is having a hump over the ideal condition. On all of this ideal condition, you can see you are having a hump. And the volume is all this pressure is rising by positive value. So you can see the pressure is rising. Here also the pressure has increased from the positive, and here also the pressure has increased. Now, since the pressure has increased from the ideal case, means the pressure that should be, suppose this you know, this is the line for P total. P total. This should be the ideal case. That should have been happen because it should follow Rod's law. But if you consider the true solution, it looks like this. And this is for non-ideal. Or specifically you can say positive deviation. Right? This is positive deviation. This graph is showing a positive deviation. How? Because the pressure that was expected, it is less. So it is more than that expected pressure. And on all these lines, you can see we have seen a rise in the pressure. So this is positive deviation. Now, if I move to this negative deviation, you can see that the pressure that was expected should looks like this, but our graph that we got from the non-ideal solution, it is looking somewhat down, or you can say a negative, a less value than the actual vapor pressure, expected vapor pressure, you can say. So this is for the non-ideal. This is P total for negative deviation. And this is the ideal case. P total for ideal case. Now, if you have seen the previous lecture, I have described how this graph is varying. So we are basically taking a pure component and then we are reducing its concentration slowly and adding x2 here, right? So initially we are having this and then suppose P naught 2, which is the pure component pressure of 2, is greater than P naught 1. So here is the component 2 which is present in the, which is only present here, you can say, because x2 is 1 here. So x2 is only present. Now slowly we are removing x2 and introducing x1. So it is decreasing because P naught 1 is less. So the effect of 1 will increase, hence the pressure will decrease. So this graph we have discussed earlier, we will not discuss it right now. Okay, so if we talk about the positive deviation, like two things should be noticed. First one, that in positive deviation, AB interaction is weaker than AA interaction. What do I mean by this? What is AB and AA interaction? So suppose we are having, initially we were having this A, only A, pure A, right? And then there was some kind, there must have been some kind of interaction between A, right? What we have done, then we have introduced a second solvent, that is B in this case, and in this case we have came to see a positive deviation. Then we will say that okay, the interaction between A and B means the introduced solute and the previous solvent that were present, and the interaction between these two is weaker than A interaction. Then in that case we will say that it is positive deviation. So suppose we see in nutshell, I want to say that if you see a positive deviation from the Rolle's law, then you will say that okay, the AB interaction is weaker than A interaction. What is the common example? It is of nitric acid and water. So how it is happening? Why is the interaction weaker? So we have two molecules. One is H2O and one is HNO3. HNO3. Okay. So initially we were having interaction between molecules, H2O molecules only, A, which will be termed as A interaction. Suppose this is A and this is A. Now what we have done, sorry, we have introduced a third party, which is B. Suppose this is a B. Now the interaction between these two, AB is more. AB, sorry, AB interaction is lesser, right? So this is okay. Sorry for this thing. So in positive deviation, we will have ethanol and water. Ethanol and water. And in negative deviation, we will have nitric acid and water. Sorry for the mistake. Again, right? The second one which we are having is ethanol. It will look like this. Ethanol C2H5. Now, if you consider the interaction here between AA and AB, two type of interactions are happening. Now, the AB interaction is of course weaker. How it is weaker? Because this bond is not, suppose this is the polarity, negative, it is positive to negative, this is the polarity and this is the polarity. The interaction is happening between these two. Suppose this is mu A and this is mu B. Now you know very well that the polarity of water, that is mu A, is greater than mu B. Why? Because the electronegative difference between this molecule is less, and this has kind of introduced a less polarity in this bond also, due to which the electrostatic interaction, which should have happened in a greater extent, has been reduced, right? And due to this reason, we have got a less polar bond in case of ethanol. and the interaction is weaker than the AA. So we can say right now that okay, the interaction is weaker and in this way it is having a positive deviation. I will show you how this less interaction results in positive deviation. That is a different thing. We'll see it one by one. But for now, consider that if we are having a kind of solution in which the AB interaction is less than A interaction, then we will see a positive deviation. And the example is ethanol and water. The second one is negative deviation. What is negative deviation? So I've told you what is negative deviation, means the pressure that was expected, we do not get that pressure. Instead, we got a less pressure, means the P total has decreased or reduced. And in this case, the AB interaction is stronger than A interaction. What it is saying that we are having the solute particles more interacted than the individual solvent particles. So we have taken the example of nitric acid and water. So if you consider the structure of nitric acid, it is very polar, much more polar than this water molecule. And it can be, you can say it can be seen from their acidity. It is highly acidic in nature, and you know very well that if something is highly acidic in nature, means it is donating H plus easier, means the electron density shifted more towards the nitrogen. That is why it is able to donate hydrogen. So this more shifting results in higher electronegativity of this bond. So this bond here, suppose it is mu b, having a dipole moment of mu b, and here we are having a dipole moment mu sa. So we will say that this mu b is greater than mu a. Due to this reason, we will have a greater dipole moment and a greater interaction between these two. Now in this case, we will say that okay, the AB interaction is greater than AA. So this is the thing that we are having. Next. Now we'll see why this interaction, lesser interaction between the AB, results in positive deviation. So I have told you earlier that the intermolecular forces between solvent and solute, in case of positive deviation, it is weaker. Solute and solvent, we can say also it as A and B. But let us clarify it. It is solute and solvent is weaker than those between solid-solid particles and solvent-solvent particles in a way. So how I am saying is that suppose the solute is A and the solvent is B. I am saying that this A and B interaction it is weaker than AA, number one. And number two, this AB interaction is less than BB also. B. And why is it so? Because of the dipole moment difference. Due to this reason, what is happening in the solution? Sorry, this is the thing. So in solution having positive deviation, now since the molecules initially were easy to escape, first of all, now the interaction AB has been reduced. So we have got a solution in which the particles are interacting less than their earlier forms. So if they're interacting less, means the force of attraction between this A and B is less. Okay. So their force is less, though if we will have a lower temperature also, then also it will get enough thermal energy to escape the solution. So did you get that point? So basically I am saying is that so initially A and B were interacting at a greater extent. Individually they were doing so. But when we mix this A and B, The interaction that we got as a result of both this A and B, that is the AB interaction or the solid-solvent interaction, that is being reduced from the previous form. So if we have to apply heat in case of suppose A to make A a phase, that was Q. Now in case of AB, we have to supply lesser heat because the force of attraction between the particles is less. So it will easily escape your vessel and become a gaseous particle. So this will increase the number of gaseous particle in above the solution, and hence the vapor pressure of that solution will also increase. So this is the positive deviation reason. The reason for the positive deviation. So in solution we have a positive deviation. The molecules of A and B find it easier to escape compared to the pure state. Pure state means AA, that was for one of the pure state, and BB, that is the another pure state of solute and solvent individually, leading to increased vapor pressure. So if we take an example, so we have this example called as methanol and acetone exhibit positive deviation. Why? Because acetone disrupts the hydrogen bonding in ethanol, weakening interaction. So you know very well that ethanol looks like this. So we have this ethanol, C2H5OH, and then we have this, say, acetone. So we have a dipole moment which looks like this. It goes from negative to positive, and here it is also negative to positive, right? But if you see this bond, the dipole moment or the electronegativity difference or the bond polarity is reduced as compared to this one, because we have carbon and oxygen here, so they are comparably less. There is a comparably less electronegativity difference as compared to this molecule. So you know hydrogen is an electropositive one, but carbon and oxygen are almost nearby in the periodic table, so the electronegativity difference comes out to be less as compared to this one, in which hydrogen is an electropositive one. So due to this reason, the interaction between this ethanol and the acetone becomes weaker as compared to the pure form, and hence the hydrogen bonding is also disrupted. So how it is disrupted? By what do you mean by disrupted? But suppose initially say we were having like this C2H5OH, we have kind of interaction C2H5, and so on, right? But when we have introduced this acetone may disrupt or come in between. Suppose the acetone comes here, right? Now the interaction is kind of disrupted. Yes. So this interaction is disturbed. Now the molecules are not interacting as well they were interacting before. Due to this reason, the molecule will be more volatile due to less interaction. So I mean to say here is that the ethanol and ethanol interaction is less as compared to is more as compared to ethanol acetone, and due to this reason the molecule find it easier to escape your solution phase and move to your vapor phase. Similarly, if we add carbon disulfide, so carbon disulfide, it looks like this: zero dipole moment, mu is equals to 0, opposite direction we have dipoles, and it is 0. If we are adding this to acetone, it results in positive deviation due to weaker in dipolar interaction between solute-solvent particles compared to solute-solute-solvent interaction. The same thing written here. So the point here I want to make is that the interaction reduces as compared to the pure form, and the molecule find it less difficult to escape the solution. The example are ethanol and acetone, water and ethanol, and then we have this carbon disulfide and acetone. So you can have these three examples. So if you are asked in the exam also with a different example, you can just imagine the interaction between those and say that, okay, so this one is having a less kind of interaction. Next. Next, we have a negative deviation. So what happens in negative deviation? So the opposite thing is happening. The first, that the interaction between A and B is more as compared to AA and BB, leading to decreased vapor pressure. So the opposite is happening here, by which I mean that now the interaction between A and B has increased. Yes. So initially A and A were interacting less, and if we apply a certain temperature, they were getting enough thermal energy to escape the solution phase, and they increase the vapor pressure by forming vapors over this solution. Now the AB interaction is more. Now if you have to say convert this A or this B into vapor, you have to supply more temperature or more heat so that it can escape that over interaction between this A and B and move to the gaseous phase to produce vapor pressure, and hence increase and hence show negative deviation, and hence they show negative deviation because the number of or the density of vapor that was forming initially in the pure form has now been reduced due to greater interaction between A and B. Okay, so if we consider the examples, we have this phenol and aniline, which has an intermolecular hydrogen bonding between the phenolic proton and the lone pair on the nitrogen atom of the aniline. So how it is happening? So let us look at it. This is phenol. This is our phenol, and this is our aniline. So there will be this kind of interaction. Now due to this interaction that is being shown here, we will see a negative deviation because now the molecules, that is molecule A and molecule B, find it difficult to escape the solution due to greater interaction, and hence it will form less vapor over the solution and result in a lowering of the graph or a negative deviation. If you want to take one more example, we have this chloroform and acetone. So this is our acetone and this is our chloroform. So if you consider these two individually, suppose we consider this individually. So chloroform is this. So initially this chloroform hydrogen must have been forming some kind of interaction, not that much, between this carbon and this H. Okay, but if you see these interaction, so and also we have this acetone. In this case, I cannot say that we can have interaction also because this acetone is having no acidic proton kind of thing. It is also not having acidic proton. I've just forcefully done it, but it is not, you can say it is negligible. It is also negligible. But now, since this H is available to interact with this hydrogen, in the case looks like this. So I can say here that we have a hydrogen that can be interacted, but in this case we do not have that electronegative element to do the hydrogen bonding for this molecule. Okay, and for this molecule I will say that we have a electronegative element, but we do not have a acidic hydrogen. But if we bring these two, they will fulfill each other wishes and do the intermolecular hydrogen bonding. So which is being shown here also. And due to this greater interaction as compared to the individuals, the chloroform or the acetone will find it more difficult to escape to the gaseous phase and increase the vapor over the solution, and hence increasing the vapor pressure. So this is the thing that we are considering about negative deviation. Now next, we will move to azeotrophs. So what are azeotrophs? So azeotrophs are binary mixture with the same composition in both liquid and vapor phase. By which I mean that suppose we take two volatile liquids and we dissolve those, it will form vapor. So suppose the composition is, suppose the mole fraction is xi for the solution and yi for the gaseous phase. It is said that the mole fraction of both this thing are same. So this is called as azeotroph, meaning the vapor phase concentration of both the component and the gaseous phase, sorry, the liquid phase concentration of both the component are same. So this is the definition of azeotrophs. So due to this reason, they cannot be separated by fractional distillation. Why? Because both of these are forming kind of vapor at the same rate. Yes, that is true. Because if they were not forming vapors at the same rate, they would not have been having equal, uh, say, vapor phase concentration. So if suppose Xi is being, say, boiling at a faster rate or converting to vapor at a faster rate than the X, Xi, I mean that X1. Suppose like this. We call it component 1 and component 2. And the mole fraction respectively are Y1, X1. In the gaseous phase for it is Y1 and the solution phase is X1. Similarly, we have Y2 and X2. So this is the two. These are the two things. Now since we have taken a volatile solution, they will form vapor and do the same thing. But suppose that X2 is more, sorry, the two component is more volatile. So it will be present in greater amount in Y2 in the above gaseous phase, and due to which Y2 will be greater than Y1. If we start boiling this thing, then the solution, then Y2 will be converted to your vapor and you can easily distill them out. But suppose this is equal, this Y2, you can say the rate of conversion of this one component and two component to their vapor phase is equal. So due to this reason, the number of particles that is formed, or the number of particles of one that is formed, is equal to the number of particles two that is formed in the vapor phase. So if you boil both of these, they will be forming vapors at the same time. So it will be difficult to distill them out or fractional or do the fractional distillation. So those who don't know what is fractional distillation, so in fractional distillation, what we do, we boil a mixture from which we have to take out our pure form, and due to the difference in their boiling point, we get the vapors one by one you can say individually, and we collect the required one as we want. Okay, so in this way we do this. So but we are saying that now the both of these are having a kind of same boiling point or nearby boiling point. Not due to this reason, the time or the moment one will start forming vapor, at the same time the other will also start forming vapor, and we cannot separate it out. Now if you consider the types of azeotrophs, there are two. The first one is minimum boiling azeotrophs and the second one is maximum boiling azeotroph. The distinction is very clear. Minimum boiling azeotroph means the one which shows positive deviation or the large positive deviation, means the azeotrophs having positive deviation from Raoult's law are called minimum boiling point, and the azeotrophs having larger negative deviation from Raoult's law are called maximum boiling azeotrophs. Okay, so if you consider the example for minimum boiling, we have this ethanol and water mixture. So they will form vapor at the same time, but their interaction is, you can say, less as compared to the original interaction, hence it will show positive deviation. And in that we have the 95% ethanol by volume. So this is, you can say, this is specific to volume also. Similarly, we have a nitric acid in water solution in which we have 68% nitric and 32% water. So in this concentration only, or at this specified concentration only, it will be acting as azeotrophs, and since it will show negative deviation, so it will be maximum boiling azeotrophs. and the boiling point is 393.5 Kelvin. So this was all about azeotrophs. At last, we are left with this topic, which is called colligative property. So in the next class, we will see this colligative property one by one. But before that, we have to understand what is colligative property. So if I say it in one liner, we will say that, okay, the property which depend upon the number of solid particles irrespective of their nature related to the total number of particles present in the solution, such properties are called colligative property, by which I mean that if we are introducing something solute in a solvent and it is affecting some property, and this property change is only dependent on the number of solute particles that we add and not on the nature of solid particles. Suppose we take two particles, solid particles A and B, and we take two different solutions, and in first solution, in first solvent we added A, and in second solvent we added B, and both of this solvent we added the same amount of solute of A and B. So we have added, suppose, 1 mole of A in solvent, and in the other solvent we added 1 mole of B. So if the property change that is happening to addition of both this solute is same, means the magnitude of the property change is having same, then we will call that property as colligative property. Okay, so this is clear. So the thing I want to make it clear is that the properties which are only and only dependent upon the number of solid particles that we have introduced and not on the nature of the solid particles, then these are called as colligative property. So if I talk about the examples that we will see, the first one we will see, it is called as relative lowering of vapor pressure. Then we have seen elevation of boiling point, depression of freezing point, and osmosis and osmotic pressure. So we will see it term by term and make it clear, the definition and the terminologies also. So let us leave it on a different class. So if I summarize our class for today, so what we have studied today, so we have basically studied the ideal and non-ideal solution. Then we have moved to this positive negative deviation, seen the azeotrophs, and seen our colligative property. So if I talk about this ideal and non-ideal solution one more time, then for ideal solution we will say that the enthalpy change is 0, entropy change is positive, volume change is 0, and intermolecular forces, IF I am representing, is negligible. Negligible. Negligible, right? Now since this delta H is 0 and delta S is 0, so if we can calculate this delta G, which is delta H minus T delta S, then we will get this value as negative. How? This is 0, right? Delta S is positive, and you know that we have taken absolute temperature, so it will be also positive. This positive result is positive, and it has a negative sign in front of it. So delta G will be negative. So this is also an important point. You should remember this also, that for ideal mixture we have this delta G negative, but for the non-ideal solution it cannot be predicted. Okay, so this is the thing that we are having between the difference between ideal and non-ideal. Okay, now non-ideal solution never follows Raoult's law, nor does it follows Henry's law. So this was the thing. Then we move towards this positive and negative deviation. So if the total pressure that we are getting from the Raoult's law is less than the actual pressure that we are getting on dissolving two things, then we will say that it is positive deviation. And if the actual pressure that we are getting is smaller than the Raoult's law as a result, then we will say that it is negative deviation. And in positive deviation we have AB interaction lesser than the A and BB interaction, and in negative deviation we have AB interaction more than the A and AB interaction. The example of this positive deviation, we have this, say we have the example of ethanol and water, and for the say For the example of negative deviation, we have this nitric acid in water. Then we move to this azeotrophs, in which I said that the solution which is having the same concentration in the vapor phase of both the components and the vapor phase in gaseous phase, sorry, the vapor the concentration in vapor phase, then we will say that okay, they are azeotrophs. I mean to say here that the concentration in both the phases, liquid and gaseous phases in a solution, if they are same, then they are called azeotrophs. And the azeotrophs which are having positive deviation, it is called maximum boiling point azeotrophs, and which is having negative deviation is called minimum azeotrophs. At last, we have seen this colligative property, which the properties which only depends upon the number of solid particles and not upon the nature of the solid particle that we have introduced. So this was for today's class. In the next class, we will see this elevation of boiling point and depression of freezing point. And with this, we will complete our lecture. Thank you.